All right, everybody. Lecture video number 3 coming at you here. Last one actually for chapter 3 as well. So going by pretty quickly with this chapter here, moving quite along. So right along to the last kind of topic we're going to touch on in this chapter here, which is on energy. Right at the very beginning of this chapter, we very quickly defined and concisely defined what chemistry is. Right, chemistry, and if go way back all the way. Let's do it. Okay, all the way back. Here we go, right? Chemistry, the study of matter and energy, right? We spent some time the last couple of classes here talking about matter and breaking that down, right? All these things talking about matter, physical properties, chemical properties, changes, all that good stuff. Now we're going to cycle right into energy, the energy section of things here, right? So first and foremost, like usual, let's go ahead and start out by actually just identifying what energy means, right? In the realm of this class in chemistry, what is energy, right? So energy, plain and simple, is the ability to do work or produce heat. Now, in any kind of situation, whenever we talk about energy, it's really important to understand this next piece here, the law of conservation. The law of conservation crops up several times this school year. If and potentially when you guys take physics, physics is another situation where you'll oftentimes see and talk about this idea of the law of conservation and its importance. But in the realm of chemistry, specifically talking about energy here, it's for any chemical reaction, energy is conserved. That means whatever energy goes into a reaction is the same amount that you get, excuse me, is the same amount of energy you get out of that. So whatever goes in, comes out in the exact same way here. Now, there are different types of energy. You can kind of break energy down in a couple of different ways. First one here is potential energy, aka stored energy, right? It's the potential energy that you might utilize in any given moment, or that might get utilized in any given moment. Maybe that's not you particularly. Next up here is kinetic energy, which is the energy of motion. And kinetic energy and potential energy are exact opposites of each other at all given times. Right? So potential energy is stored energy that is being stored away and not being utilized, whereas kinetic energy is the energy of motion. It's utilizing that stored potential energy to then create kinetic energy in that particular way. Okay, heat. Now, heat is another type of energy specifically that we're going to talk about oftentimes in this class. It's energy that is in the process of moving from a warmer object to or towards a cooler object. So it's very specific what energy is in terms of heat. When we talk about heat energy, it's in the process of moving from a warmer object to a colder object. So pretty much everything in this world, dictates that idea of being, whenever an object is warmer, it's always going to constantly cool off and whatnot. And one thing that we actually will talk very briefly about at some point is the idea that there really is no idea actual science definition for something called cold. Things are cold because it lacks heat. So heat is really just the only thing that transfers to and from objects. So when something is very, very cold, when we describe it as being cold, it's actually something that lacks heat, right? So heat is the measurable thing. You can't actually measure how cold something is, it's just a lack of heat. All right, so next up here is the different types of energy. Now, there's going to be a energy we talk about. Again, heat energy is going to be the one we focus the most on, especially with regards to the rest of chapter 3 here. But there are going to be a few other ones that we touch on as this class progresses. Starting, of course, with chemical energy, right? You guys are obviously taking chemistry. Of course, there's going to be something called chemical energy. Chemical energy, more often than not, though, is a stored type of energy. It's an energy that gets stored away in a chemical reaction and doesn't really get utilized until a reaction occurs. That's why it's also sometimes just called potential energy, because it's that stored energy we talked about just a moment ago. Next up here is electrical energy. There's also electromagnetic energy, which is different than electrical energy. So electrical and electromagnetic are very different. They are your light or radio or microwaves. Mechanical energy, right? Again, mechanical energy is a very, very hot topic, especially in physics class. You guys talk probably pretty much the entire half of the school year talking about mechanics in physics, talking about mechanics. That's really just the energy of motion. There's also nuclear energy. There's lots of energy stored away in nuclear reactions. Thermal energy, which is a type of heat energy that we're talking about. It's kind of that same realm here, and that's going to kind of be what we focus on here. Thermal energy is associated with the random motion of particles in a sample or just a sample of gas more specifically too. But it's really just the motion of particles. If something has a really, really high amount of thermal energy, the motion of those particles are moving very, very fastly, right? Thinking back to our particle diagram. So if those particles in a particle diagram moving very, very fast, high thermal energy. If they're moving very, very slowly or just kind of vibrating next to each other, very, very low thermal energy. Now, how do we measure this idea of heat or this idea of thermal energy? It's actually pretty simple. We use it utilizing this unit here called joule, Joule, capital J, joule, right? Just kind of like the joule on your if you've got a ring, for example, right, or a chain, right? Might have some joules in your chain. It's kind of the exact same thing, right? Joule, and that is the unit for energy. There is another one here called the calorie, which is the CAL. It sounds kind of similar to the calories that we intake whenever we eat food and drink certain things, right? But there's a little bit of a difference between this calorie, which is lowercase CAL, versus the other calorie, which is actually capital CAL. So I know it's very confusing sounding, but they are a little bit different. So don't stress too much though, because we're not going to really talk about the other calorie, capital CAL. We're going to mostly talk about this one, lowercase CAL here. Now the conversion between calories and joules here is pretty simple. For every 1 calorie you have, you've got 4.18 joules. So if you've got 2 calories, 2 times 4.18 gets you the amount of joules, right? So you can kind of convert between those two very easily when it comes to, I'll backtrack for a second. You can kind of convert between those two pretty easily whenever you need to. But more often than not, guys, we are going to really be focusing a lot of our attention right here on this 4.18 joules. More often than not, joules is going to be our main form of kind of measuring, a unit for energy here. Now, speaking of, is something called specific heat. Now, specific heat, plain and simple, is the amount of heat required to raise the temperature of a substance by 1 degree Celsius. It kind of sounds like a lot, but it's a lot more sort of easy to understand than that. The abbreviation for specific heat is going to be a lowercase c here. Now, let's talk real quick. So, specific heat, the amount of heat required to raise the temperature of a substance by 1 degree Celsius. Okay, let's break that down. So what that means is if you need to increase the temperature of a substance, let's say from 10 degrees Celsius up to 20 degrees Celsius, let's say a body of water, where you want to heat up your body of water from 10 degrees Celsius to 20 degrees Celsius. It's going to take a substantial amount of energy to raise that up, right? Inputting a substantial amount of thermal energy into our body of water to raise it from 10 degrees Celsius to 20 degrees Celsius, right? And you can actually do a calculation in just a second that I'm going to show you the formula of, to show you kind of how you do that and how much energy actually needs to be inputted based on the substance and based on how many degrees you want to increase or actually also decrease too. This table here, 15.2, has a really good, nice, concise list of a bunch of different substances and their states of matter, as well as their specific heats. And you can kind of tell that water as a liquid here, it's water with an L in parentheses there, has a very, very high specific heat, right? Think about the bodies of water you would have swam in. Like if you've ever swam in the Atlantic or the Pacific Ocean, or maybe even any of the lakes nearby here, Lake Erie or Lake Ontario, right? The temperature of those lakes don't really change all that drastically from day to day versus air, for example, right? Air, right, that we breathe every single day has a very, very low specific heat, right? It doesn't take much energy to change the temperature of the air we all kind of live and breathe in and whatnot. That's why temperature changes fluctuate across a given day, anywhere between 10 to 15, sometimes even 20 degrees Fahrenheit. Whereas whenever you talk about bodies of water, they only change a few, maybe even less than that, like 0.5 degrees Fahrenheit, maybe even 1 degree Fahrenheit across a day. So specific heat is dependent on how much energy needs to be inputted into a substance to change the temperature of it. Now, like I said, every substance has a different specific heat, so we're going to kind of just reference 15.2 again here. But moving on now to measuring heat. Well, how do we do that? Okay, how do we measure heat? Pretty simple. We have a new formula to add to our repertoire here. And yes, before you even think about anything, the reference table I gave you guys the other day for your first quiz does have this in it, right? This formula here, Q equals MC delta. That delta symbol is a triangle. You might have referenced it in the past. We'll talk more about it in the future here, okay? Breaking down each part of this formula here, the first one here is the Q. Q is your amount of heat, right? It's the amount of heat available or essentially necessary to actually change your temperature, right? And the unit for this is going to be uppercase J, or that joule again. Next here is lowercase m, which is of course going to be mass measured in grams. Next up here is that lowercase c, that specific heat of that substance that we just referenced in the previous slide here, specific heat. And then delta T. Now, delta just is a fancy way of saying change in something, right? So the change in something based on an initial and a final measurement, right? So in this case here, since we're talking delta T, T is referencing temperature. So it's a change in the temperature from the initial, what it was read at initially, and the final temperature that was read afterwards. This equation can be used to measure the amount of heat absorbed or released by a substance. And we're going to do a couple of different examples of this formula going into next class. Now, a couple of things, though, to note before I kind of close off this video. Whenever you finalize your answer, let's say you are solving for Q in a particular way. Let's say your Q value for heat in joules is positive 1,000 joules, right? If you have a positive value for Q, that means whatever substance you're talking about, water, steel, carbon, if it's a positive value for Q, that means that that substance, that water, that steel, whatever, absorbed heat, which means the temperature of it went up. Because if you guys absorb heat, for example, the body temperature for you guys is going to go up, right? But on the flip side here, let's say you calculated something with this formula here, and the measured value for Q you got is negative 500, right? Negative 500 joules. That means that heat was released. That means the body you're referring to, your body of water, your sample of steel, your sample of carbon, it released heat, it lost heat. So if you lose heat, that means yourself is going to, your body, the thing you're studying, if it loses heat, its temperature is going to go down. So we're going to kind of relate that between the temperature measurements you kind of, see before and after, right? That initial and that final temperature you see right here for your delta T formula. You're going to see how the changes in temperature, whether the temperature goes up or goes down, affects the overall value of your Q, whether it's positive or negative. So again, when I see you guys next, we're going to talk about this formula a lot, do some examples of it, and then kind of close up this chapter. Thanks, guys. See ya.